So we're going to start our penultimate lecture on fluids. We are going to actually start making fluids move, which obviously makes things harder when things move. But luckily, there's an equation that makes this pretty straightforward. It's just a lot to keep track of. Let's start with our learning targets, in that I can define laminar flow and mass continuity. So we'll talk about both the word laminar as well as continuity, and that leads to our next learning target. I can derive the continuity equation. I can solve problems both qualitatively and quantitatively about continuity, and I flipped those words, sorry, but hopefully that makes sense. I can derive Bernoulli's equation, so Bernoulli's equation will have a lot to do with the continuity equation that we talk about. And then I can use Bernoulli's equation to solve for variables for a fluid in motion. So Bernoulli's equation and the continuity equation are both for fluids that are going to be in motion. And once again, the continuity equation is quite complex, just because of how many terms are in it, but it really is not that difficult. At least I'm hoping that you agree with that. So if we consider a fluid that flows smoothly with no friction, that kind of flow is called laminar flow. So the mass flow rate is going to be the mass that passes a given area per unit time, that unit time being some delta t. And the mass flow rate has to be the same as it crosses any area as long as no fluid is added or removed. So this is kind of similar to mass conservation. It's just called mass continuity in fluids. So the mass in a bottle, for example, of water, if it's flowing, whether it's going through the body of the bottle or whether it's going through the neck of the bottle, the mass has to be the same. So that mass flow rate is going to also be the same as it crosses any area, as long as we are not taking away from the fluid, and we are not doing that. All of what we are assuming for the continuity equation is that the mass of the fluid is going to remain the same throughout. So I will say this is a bit of a long derivation, but we are going to do it. So I will start here and it'll continue to the next page. So we know our first thing, that mass is equal to density times volume. And if I look at my bottle here, I can also say, okay, well, I know that volume is going to be the area times one of these distances, x. So I'm going to actually write this as ax, and it'll make sense why I do that shortly. Now, x here, I know this is some kind of displacement, and so if I think about displacement in terms of velocity, I know that velocity is equal to the change in x over some time interval. So this is a bit of a jump here. Let's say we have m divided by delta t is equal to rho a x divided by delta t. So all I've done is divide both sides by delta t, and it'll become obvious pretty quickly why I did that. But the hard part about these equations is these derivations in terms of seeing where to actually go next. And you'll never actually have to derive them. I just think it's kind of cool to look at how they come about, so that's why I do it. So if we look at this, we could say, okay, x over t, I know that that is equal to velocity, so that means that my mass flow rate, this m over delta t, is going to be equal to the density times area times velocity. And this is where this is going to get confusing, and that we have both velocity and volume in our problems. So just to keep it in mind and keep it in the back of your head, that make sure you're clear about which one is which. I'm sure that you'll mess it up at some point. I have messed it up at multiple points in my career. Remember, fluids was kind of my thing in college. It was something that I really, really enjoyed doing, so I have messed this up more times than you will ever do in your stay in this class. So we know that the mass that flows past any point is given by m over delta t is equal to rho AV. So that means that if that's the case, then rho 1 A1 V1 should be equal to rho 2 A2 V2, because the mass that's flowing through this area should be equal to the mass rate of that area, and we know that the mass rate is equal to rho AV. So we also know that the fluid is incompressible, and that's very important to know because that means, let me write out incompressible. That means that the density is not changing, so these two go away. So we have A1 V1 equals A2 V2, remembering that those are velocities, not volumes, okay? This is a very, very important equation. Once again, this is your continuity equation. Going to become very important, and especially in conjunction with Bernoulli's principle, which has, like I said, has a lot of terms, but we will get to that. So if we think about the continuity equation, once again, let me just write it down. So for any fluid that is incompressible, density is obviously going to be the same. So density doesn't typically change in liquids. So that means where a pipe is wider, the flow is going to be slower. So you could see that in a river. So if you look at the flow where the river is wide, you could see it's very slow. The water is not going to move a lot. But if you have an opening in the river where it's narrow, the water's going to flow a lot faster in that as opposed to the bigger river on the left here. I should say wider river, sorry. So we're going to talk about a few, we'll do a couple examples here before we move on to the next part of our lecture. So water flows at a constant speed through one section of a pipe. When it enters another section that has half the cross-sectional area, what happens to the speed of that water? So a lot of times with our continuity equation, and I know the answer to this is probably obvious, but bear with me. A lot of times with our continuity equation, this 1 and 2, I'm going to encourage you that this is going to be in and this is going to be out. Okay? And if you think about it that way, these problems become a lot similar as opposed to you saying, oh, what one is 1 and what one is 2. It doesn't matter, as always, as long as you're consistent. Okay? So I know that A2 is equal to A1 over 2. Okay, so it's probably obvious that the velocity of in this second half of the water is going to be double, but I'm going to write it out anyway. So A1 V1, so this is what was in, is going to be equal to A1 2. So that's A2 just written as a function of A1 times V2. These cancel, so V2 equals to V1. Water flows through a pipe of cross-sectional area 10 square centimeters at a rate of 15 meters per second. So you'll look at this and you'll look at this and think you have to convert. You actually don't, because both of your areas are in centimeters, so they're going to cancel out. And it's important to recognize that sooner rather than later, so that you don't waste the time converting. We all know about what a time crunch AP is and getting to every question. So the cross-sectional area of the pipe is going to be decreased to 5 centimeters squared. So this is, you can also think about in versus out as initial and final as well if you want, in the event that we're talking about the same pipe, like in this case here. So what is the water rate or the velocity of in the narrow section of the pipe? So if I say, okay, A1 V1 equals A2 V2, I'm looking for V2, that being the second section after I've changed something. So V2 is equal to A1 V1 over A2. The area of the first one was 10 centimeters squared. And the area, or the velocity rather, that the water flowed with is 15 meters per second. The area of the pipe gets decreased by a factor of 2. So we are left with a doubling of speed, very similar to what was shown in the previous problem. Okay. Do one more example, and then we're going to move on to more things about fluid flowing and Bernoulli's equation. So water flows through two pipes that connect into one larger pipe. The speed in the two pipes is 10 meters per second, and they each have a radius of 5 centimeters. The larger pipe has a radius of 15 centimeters. What is the speed of the water in the larger pipe? Okay, so we have to take into consideration that this is a tube and this is a tube. So if we say, okay, A1 V1 is equal to A2 V2, this A1 is the sum of these two areas. So we have to add this one, which is pi r1 squared, let's call it, and this is pi r1 squared. Okay, so, and we are solving for V2 once again. So V2, we remember from previous problems, I'm going to write up here, is equal to A1 V1 over A2. So V2 equals pi r1 squared plus pi r1 squared. Again, just adding the two areas, or the areas of both of these, times V1 divided by, let me call this pi r2 squared, which is just the area of this, so pi r2 squared. Okay, pi cancels, as we know, because I could just factor pi out of that. So this is 2r1 squared v1 divided by r2 squared. So this is 5 centimeters squared times 10 meters per second divided by 15 centimeters squared, and you should get 2.222 meters per second. Okay. So fluids in motion and Bernoulli's equation. So once again, this isn't necessarily super complicated, but it's a rough derivation, and it is a lot of terms to remember. So just bear with me throughout this. So when a fluid moves through a pipe that gets narrower, it speeds up. But where does that increase in kinetic energy come from? So what's actually happening in order for the kinetic energy to increase? So we considered pressure that can differ between two openings. However, fluids can also change in height. Okay, so it's not the pressure that's necessarily causing this increase in kinetic energy, but if we think about the height, the object, when it's at this height versus this height, is going to have a difference in speed. Okay, so the total mechanical energy of the fluid is going to remain constant unless work is actually done by it by some net force or pressure difference. Okay, so if we were to write this out, any external work plus gravitational potential energy plus kinetic energy is going to be constant. Okay. So we're looking at a fluid. So let's look at each term per unit volume. So again, this is a really big jump to just get used to thinking about this. But if we do that, it does make this a lot easier. Sorry, I didn't mean to put equals. I meant to put a plus sign here. Give me 1 second. So this is going to be mv squared. Okay. Oh, divided by v. That's what I'm missing. Okay, sorry. Okay. Now this is very confusing because this is velocity here. Okay. But this is volume, and we're gonna get rid of the volume in a second here, which will help. You can see mass over volume is going to become density, but I know that it's very confusing to see. Maybe I should use a different color when I'm doing this. I might do that. So just remember that this is a constant. Okay. So if I rewrite this, and the work that's actually done, remember work is equal to force times distance, and this is over v, plus rho gy plus 1/2 rho v squared is going to be a constant, okay? Stop for a second and then I'll keep going, even though I know you probably paused the video at this point. Okay. So if we continue with what we were saying, our last step here was Fd over V, remember that's volume, plus rho gy plus 1/2 rho v squared is constant, remember, okay? If we're looking at a pipe, for example, okay, a pipe that has some, that was awful, I apologize, a pipe that has some area A over some distance D, then we know that volume is equal to AD, okay? So that will help us out. I'm going to plug that in here. So this is FD AD plus rho gy plus 1/2 rho v squared is going to be a constant. Okay. Cancels. And I can look force over area. That's perfect. That's pressure. So pressure plus rho gy plus 1/2 rho v squared is a constant. And this is what is called Bernoulli's equation. So, a lot of the problems that you are going to see, a pipe is going to be changing diameter and height, or height. It could be really doing both, right? So anytime that the pipe changes shape, you're going to be able to figure out, because of continuity, what any of these variables actually are. So what this ends up looking like, if everything stays constant, then the pressure at 1 plus rho gy1. Remember, rho is the same because we're talking about a fluid that is not changing density. We're talking about an incompressible fluid. Plus 1/2 rho v1 squared is going to be equal to P2 plus rho gy2 plus 1/2 rho v2 squared. So this is an equation, this relationship you are going to use very often, and that's why I said it does have a lot of terms, but hopefully they're not complex terms. It's just a lot to keep track of. So you have your pressure term, you have your gravitational potential energy term, and you have your kinetic energy term here, and they need to be equal for both of them. So it's just a lot to keep track of. Okay. So if we talk about the next thing, if we talk about horizontal flow, H is not going to change, so that actually makes things a lot easier. So P is going to be P plus 1/2 rho v squared plus rho gy is going to be constant, as we know, because that's Bernoulli's equation. But this is going to go away because there's no change in y. Okay? So as the fluid speed increases, the pressure is going to decrease. And it's going to be important to note that A1 V1 is equal to A2 V2. That's still going to hold true even if there is a change in elevation that has nothing to do with that change in elevation, because at the end of the day, that is a continuity equation that only has to do with the fact that mass is a conserved quantity. So, um, this is a really, I read a lot about this, and in AP training, they talked a lot about this. So if you're given a multiple choice question involving Bernoulli's equation on the exam, a lot of times it's advised to skip that one and go back to it just because of the sheer amount of time that they take, just because it is so many terms. Okay, so a couple of notes on problem solving with Bernoulli's equation. So that continuity equation, once again, is going to hold true even if there's a change in elevation. So sometimes you're going to need to solve for a second velocity using that equation and then plug that into Bernoulli's equation. So you're starting with one thing and going on to another. When you're given the change in pipe radius or diameter, make sure you're going to actually calculate the change in cross-sectional area. So remember, cross-sectional area for a pipe is pi r squared. And then if the diameter doubles, you simply cannot double the area. It would be increased by a factor of 4, okay? So let's say you have radii instead. You could say, okay, a1 v1 equals a2 v2. So pi r1 squared v1 is equal to pi r2 squared v2. That would mean that if you're solving for the second velocity, which again is what you're solving for a lot in these problems, is equal to v1 r1 squared divided by r2 squared, just in case you want that relationship readily available, just to give you an idea of that. So let's keep going. Okay, so I will remember why I actually wanted to talk about this once we get there. Maybe I won't. Okay, so you can, so if I look at pressure, if I turn the water on, I know that the level is going to rise, right? I turn the water off, it stops. I can remove this, right? Okay, so if I look at the flow tab here, so this is really cool in the sense that you can look at how the water is actually going to change. So right now we have a flow rate of 5,000 liters per second, so we know that that's a volume per second. Now let's say that I constrict the flow here, right? What happens to the particles here? They start moving a lot faster, right? Hopefully that makes sense. Or if I do this, you could see that the particles start moving a lot slower toward the top here, okay? And it's very obvious here as well with these dots that are all just pouring out, but you could definitely see that it's going to get a lot slower there. And then if I increase this here, okay, so however you do this, you're going to be able to see, you could play around with it a bunch if you want. You could see how the molecules change. I'm obviously very distracted because I was interested in playing around with this, but, and then if, oh, this I'm not going to go into because this is going to be our next thing that we do. So, but hopefully this is interesting enough. Once again, I think it's pretty cool. So, I'm not positive how to use the speed thing. I was hoping I was going to be able to, but it was not. It's not letting me. So, okay, we will move on from that. Otherwise, I'll be distracted for a while with that. Okay. So, we'll move on to our last few examples in this. A couple of them will take, these will take a bit of time, so just bear with me as I try and explain them. So a pipe has 3 different sections with 3 different cross-sectional areas. Where is the pressure going to be the least? So you may be able to look at this and just give an answer, but I'm actually going to do this out. And again, this is going to be pretty long. I'm going to note up here A1 V1 equals A2 V2, which means V2 is A1 V1 over A2. Okay, that will come in handy as we move along here. So all that we really know, unfortunately, are the pressures and the relationships between the velocity and the area. So if I write Bernoulli's equation, I could say, okay, Not going to state all these terms, but you know that they're all here. Cool thing about this is this term and this term go away, and they wouldn't always, but this is horizontal flow, and so y is not changing. Okay, these are all these barometers are all at the same height. So if I start taking a look at this, I could say, okay, well, P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. Okay, so if I say, all right, well, P1 minus P2 is going to be equal to 1/2 rho V1 squared, sorry, V2 squared. Yep, P2 squared, or V2 squared rather, minus V1 squared. Now, this is complicated because I don't actually know V2. However, I know that they're related like this. So then P1 minus P2 is equal to 1/2 rho A1 squared V1 squared over A2 squared minus V1 squared. So this is P1 minus P2 equals 1/2 rho V1 squared A1 squared over A2 squared minus 1. Okay, this on this side, because A1 is clearly bigger than A2, that's going to be a positive number. Okay, so this is a positive number. That must mean that P1 is going to be greater than P2. So that's important to know. So we know P1 is greater than P2. Okay. That doesn't actually solve our problem just yet, unfortunately, because now we have to look as the fluid goes from P2 to P3, how does that actually look for our equation, and will P3 or P2 be greater? Once again, you probably could have looked at this and just determined that P2 is going to be the least amount of pressure, but let's run through this. So if I'm now going from 2 to 3, I could say by the continuity equation, okay, V3 is going to be equal to A2 V2 over A3. So once again, with continuity equation, it's horizontal flow, so I am reduced to this equation again. I'm going to write it in terms of 2's and 3's though, so P2 plus 1/2 rho V2 squared equals P3 plus 1/2 rho V3 squared. And I'm going to say, okay, P2 minus P3 is equal to 1/2 rho V3 squared. Sorry. Write that a bit better. V3 squared minus V2 squared. Okay, and now I'm going to plug this in for V3, so P2 minus P3 is equal to 1/2 rho V2 squared A2 squared over A3 squared minus V2 squared. So this ends up with the same reduction as above, and that 1/2 rho V2 squared A2 squared over A3 squared minus 1. However, we know A2 is less than A3, so this here on this side is now going to be a negative number. So if that's a negative number, that must mean that P3 is bigger than P2. So that means that if P1 and P3 are both bigger than P2, then P2 has to be the smallest. I know that I have written all over the page here and that it was probably extremely hard to follow quickly, so I apologize for that, but hopefully it makes sense. We've got 2 more examples and then we will be on to our easy lecture. The water flows through a horizontal pipe at a speed of 10 meters per second and a pressure of 250,000 pascals. The pipe narrows and the water speed goes up to 20 meters per second. So what is the pressure in the narrow section of the pipe? So first thing that we notice, this is a horizontal pipe, and that's very important because that's nice to know, because that means that one of our terms in Bernoulli's equation is going to go away. But I will write out the whole thing just for the sake of actually seeing that. So P1 plus rho gy plus 1/2 rho v1 squared is equal to P2 plus rho gy plus 1/2 rho v2 squared. Now what's important to note here, we're talking about a horizontal pipe, right? So if I look at this, what's happening to it is it's decreasing in diameter, right? Because it's speeding up. So I'm calling over here, this is 1 and this is 2. Again, just like initial and final conditions, or if you want to call this in and out, however you want to look at it, it doesn't matter. It's all the same. You just need to know and keep consistent with what you define as what. So these are going to go away because it's a horizontal pipe. So then I'm left with P1 plus 1/2 rho v1 squared is equal to P2 plus 1/2 rho v2 squared. And I'm trying to solve for the pressure in the narrow section of the pipe. So that's P2, so I can say, okay, well then P1 plus 1/2 rho v1 squared minus v2 squared. I just combined my terms. If that's confusing, just pause this and go through why that's the case. I subtracted this term from this term, right? And then just combined them, okay, is equal to P2. So this is 2.5 times 10 to the 5 pascals plus 1/2, and it's water flowing through, so 1,000 kilograms per cubic meter times the velocity at 1, we're told, is 10 meters per second. 10 meters per second. And that's squared, minus 20 meters per second. And that's also squared. So you will get an answer of 10 to the 5 pascals. And hopefully that makes sense. This is one that once you get used to these problems, you wouldn't have actually had to do that out, because you know that the pressure in section 2 is going to be less than the pressure in section 1. So the only possible answer for that was A. So once you start getting used to these problems, you'll save yourself a lot of time by just being able to recognize that. It obviously does take a lot of time for that to be the case, just like any other physics problems, but hopefully you get there sooner rather than later. Okay, our last example for this particular note packet. So water flows through a horizontal pipe area of 2 meters per second squared at a speed of 10 meters per second and a pressure of 4.5 times 10 to the 5 pascals. The pipe narrows to 1 square centimeter and goes up to a height of 20 meters. What is the pressure in the narrow section of the tube? Okay. So I'm going to write down some things that I know. So I'm going to say, okay, I know that A1 is equal to 2 meters squared. I know that V1 is equal to 10 meters per second. And I know that P1 is equal to 4.5 times 10 to the 5 pascals. And the only reason that I'm really writing these this time is because I was given a lot of numbers, and I don't like a lot of numbers, so I like writing them down to actually figure out what I have. I encourage you to do this as well if you're having a hard time keeping track of everything. So A2, I'm told, is 1 meter squared. V2, I actually don't know, but the nice thing is I can use the continuity equation to figure it out. And we'll do that after. We're trying to solve for P2. So that's why we need our continuity equation, because here we have 2 unknowns, but Bernoulli's equation is only one equation. So by employing the continuity equation, we have two equations, two unknowns. Okay. So whether you want to plug this in now or not, I'm not going to, just in case you didn't have numbers with this. I want you to see it with the algebra rather than see it with just a bunch of numbers. So I'm going to leave V2 as this. It will look messier, but bear with me. So my Bernoulli's equation P1 plus rho g y1. Oh, that's another thing. Y1 is equal to 0. And then it goes to a height of 20 meters. Okay. Plus 1/2 rho v1 squared is equal to p2 plus rho gy2 plus 1/2 rho v2 squared. So this term is going to go away because it started on the ground, and I know it doesn't explicitly say that, but the fact that they didn't tell you it starts at a shorter height, or at any height whatsoever, you can assume that it started at the ground. Most times AP problems will actually state that. This is a problem that I took from a book, so it doesn't actually tell you that, but hopefully you believe me that it did start at 0. So now I'm trying to solve for P2 here, so I'm going to actually rearrange this before I start plugging in numbers. So P2 is equal to P1 plus 1/2 rho v1 squared minus v2 squared minus rho gy2. Okay. And again, if you need to do the algebra out, you go for it. I had room on my paper, but obviously on the computer, it's not as easy to have the space to write all of that out. So when I do this, once again, I don't know V2, but I do have a relationship for V2 as a function of variables that I do know. So P2 is equal to P1 plus 1/2 rho V1 squared minus A1 squared V1 squared over V2, or I'm sorry, over A2 squared minus rho g y2. And I'm going to write this a little bit more condensed. So this is P1 plus 1/2 rho V1 squared 1 minus A1 squared over A2 squared minus rho gy2. And now I have all of these variables. This is just a matter of plugging in numbers. So once again, because the pipe shrunk, hopefully it makes sense that the pressure will be less. However, you actually can't single that out because all of these pressures are less. So that makes this a bit more challenging as well, in that you actually have to solve for it. So 4.5 times 10 to the 5 pascals plus 1/2 times 1,000 kilogram per meter cubed times 10 meters per second squared times 1 minus my ratio of areas squared. And that's also times 20 meters. Sorry, I'm running out of space. And that is equal to 1.04 times 10 to the 5 pascals. Once again, kind of a longer lecture, but luckily you have the weekend to work on this one, so hopefully not too much of a issue. Okay, one more lecture in this unit, and then you are done with at-home stuff for the most part, which is kind of nice.